In this video, we're going to explore a few more reactions with alkenes. The three reactions we're going to explore in this video are going to be hydrogenation, and these are all generally addition reactions to alkenes. So hydrogenation will be the first one, the second one will be epoxidation, and the third one will be ozonolysis. So let's look at this first one first, hydrogenation. So the general reaction for hydrogenation is going to be the addition of H2 across a double bond. And this is usually catalyzed by platinum, palladium, ruthenium, any number of metals, usually platinum or palladium. And then, as you can imagine, it adds H across the double bond. The metal catalyst is required to speed it up. Without the metal catalyst, this is usually so slow that it's not really realistic on a laboratory timescale. But with the platinum or palladium, sometimes supported by carbon catalyst, this goes pretty easily and pretty quickly. So what this looks like in a reaction, say we have an internal trans 2-butene. We're going to add H2 on palladium, say palladium on carbon. And this will reduce the alkene to the alkane. So we go from butene, so to butene to butane. So you can see we've net added an H across the double bond. This is non-specific, so it will reduce all double bonds in the molecule. So say we have this molecule here with 3 double bonds. If we do this in an excess of H2, and this time I'll do it on platinum, we will reduce all of the double bonds to single bonds. It is non-specific. It will not, however, reduce the double bonds in the benzene ring. So if we had this reaction here, we had H2 on platinum, it would leave the double bonds in the benzene ring, but reduce the external double bonds. So we'd end up with ethyl benzene. From styrene, we wouldn't reduce the double bonds in the benzene ring. The stereochemistry of this is a syn addition. So this is a syn addition, similar to hydroboration or oxymercuration. So if we draw an alkene that has a stereochemistry or is prochiral, we added H2 on palladium on carbon. If we examine this, if I put one H like this and one H down, we'd have a methyl, we'd have an ethyl going back, and we'd have a bromide going back, and we'd have a methyl pointing forward. So we'd have the H's at, this is actually backwards. We'd have the H's add syn to one another, and that's because the mechanism dictates that the H's are not added at the same time, but they are added on the same face of the double bond. So this bromide would be facing backwards, this methyl would be facing up. And if we rotate this, so this would be in the plane, this would look something like this, where we'd have the methyl facing back and the bromide facing back. So you can see that there's an up H, there's an H that's been added here, and there's an H that's been added here. So it's a syn addition of H2 across a double bond. And that really only matters when there's stereochemistry involved, but it will be on the same side of the double bond. So hydrogenation, very powerful reducing agent. It will take double bonds down. It will reduce an alkene to an alkane. Turns out it will also, which we'll see in a later chapter, it will reduce an alkyne to an alkane as well. So the next one we're going to look at is epoxidation. So epoxidation is a new functional group that we haven't seen before. So if we look at H3C, CH3, this would be ethane. If we look at H2C, CH2, this would be ethene. An epoxide is a derivative of an alkene where you have a cyclic structure with an oxygen. So this is what we would call epoxy, ethane. So this structure here, where we have a cyclic structure with an oxygen bonded to 2 carbons, is what we call an epoxide. So epoxides are formed by reactions with peroxy acids. So we already saw that this functional group, COOH, so this is COOH, or CO2H. This is what we saw before, is called our carboxylic acid. If we add another O right here, instead of RCOOH, we have RCOOOH. Oh, I'm sorry, that's one too many O's. Got carried away there. RCOOOH, we have what's called a peroxy acid. So this is sometimes abbreviated as RCOOOH or RCO3H. So this would be R groups. And this is called not a carboxylic acid, but a peroxy acid. So common peroxy acids are where this R group is methyl. So this is called peroxy acetic acid. Another common one that's a specialized reagent, but used in particular for epoxidation, is this peroxy acid here, which is called metachloroperoxybenzoic acid, or abbreviated as MCPBA. So MCPBA would be an appropriate epoxidizing agent to write on an exam, for instance. So using these two reagents, we can convert alkenes into epoxide. So let's look at what that general reaction would look like. So again, we're transforming a CC double bond into a COC cyclic structure. So what we have is we have a C double bond C. We add a peroxy acid. And what we get is the epoxide, and we're left with a carboxylic acid. So we've transferred, essentially, it ends up being this O. We've transferred an oxygen to the double bond. So functionally, what this would look like is you could either write peroxyacetic acid, you could also write MCPBA, both would be acceptable. And you end up with the epoxide, so we transform this alkene into an epoxide functionality. Notice stereochemistry stays. So if we have a cis double bond, we add MCPBA, we will still have cis methyl groups, so they're going to be on the same side. So cis stays cis, trans stays trans. I'm going to go over the mechanism. It's not one that you necessarily have to know, but it does show an interesting concerted mechanism that we haven't seen before. So I'm going to draw this structure in a specific way. So here we have our alkene and our peroxy acid. So what we see is that we have this bond transfer here, this bond transfer here. So this is our O that gets transferred. We push this bond out, and this bond grabs the H. So it ends up being a 4-step mechanism. If we're drawing the transition state here, we have a partial, our double bond is going away. We have a partial bond to an oxygen. The hydrogen is being transferred. This O bond is breaking. This double bond is forming. This double bond is breaking. We have a partial bond here and R. This would be our transition state. And what we'd be left with is the epoxide plus, if we draw this in the way that we drew it up there, the carboxylic acid that is released. Not necessary that you can redraw this reaction mechanism, just interesting to see if you're interested, and it would be important moving forward in chemistry classes. So the final reaction I want to talk about is ozonolysis. So there's two parts of ozonolysis. There's ozone and lysis. Ozone is O3, which we see as the structure has an interesting structure. We write a Lewis structure of ozone. We see that we have a positive and a negative charge, and that exhibits resonance, where we have the negative charge distributed across the terminal oxygens and the positive charge localized on the internal oxygen. So what this means is ozone is a very powerful electrophile. So we have an electrophile at this central oxygen atom. That means it's very reactive towards things like alkenes or other nucleophiles. The other portion of ozonolysis is lysis, which means breaking apart. So what we're going to do is we're going to use ozone, O3, to actually break apart double bonds. So in a generic sense, what we see, we have our alkene. This is another two-step process. We had ozone in the first step, And then the second step, we had H2O or Me2S, either one. And what we get is that we break this double bond right down the center, and we replace it with oxygens. So you can see that the double bond was once here and has now been replaced with double bonded to oxygen. So we've essentially lysed that bond. So an example of this would be if we look at this structure here. So we do ozonolysis. So first step, ozone. Second step, Me2S or H2O. So again, we're going to take this double bond and we're going to break it right down the middle. We're going to insert two O's on either side. Note that this is going to turn into an aldehyde. This will turn into a ketone. So if I draw it just to make sure it looks the same, so we draw OO, this is an H, or if we want to rotate these around, we end up with acetone and this aldehyde, so we end up with two products. So ozonolysis will cut a double bond, so if it's a linear alkene, you will end up with two different products. However, if we have a cyclic alkene, you will end up with a linear alkene. So if we do ozonolysis on this species, this methyl cyclohexene, so I'll do H2O, we're going to cut this double bond, and it's going to form two carbonyls. However, if we count, we go 1, 2, 3, 4, 5, 6. So they're going to be connected around the back, and there's going to be a carbonyl at carbon 1 and a carbonyl at carbon 6. All right, so what we see, if we start at carbon 1, and the other substituent here is an H, so we have an H, we have a carbonyl, that's carbon 1, 2, 3, 4, 5, 6. We have another carbonyl, and then we have that methyl group that's hanging off the end. So if we have a cyclic alkene, we're going to end up with a linear alkene. If we have a linear alkene, we're going to end up with two alkenes that are separate. So ozonolysis is a very powerful reaction, as is epoxidation and hydrogenation. And both can be used, all three can be used actually in more complicated synthesis.